Hello. So today I'm going to be talking about electric drive propulsion and free energy. I'm Dr. Mike McCulloch from the University of Plymouth in the UK. So the talk is going to be divided into a few sections. So I'm going to first discuss what inertia might be, introduce quantized inertia, astronomical evidence for it, some lab evidence, and then I'll discuss why QI or quantized inertia means we can get new energy from information. And throughout the talk, I'd just like you to remember that there is something called a horizon. This is a picture of me in a kayak at sea, but you can see there is a boundary called a horizon beyond which we cannot see. And this does not just apply to visible light. This applies to any electromagnetic radiation or any information as well. And that will become more relevant later on. Okay, so just a brief summary of my background. So I have a BSc in physics from the University of York in the UK, PhD in ocean physics from Liverpool. I was a scientist at the Met Office for 10 years, and I'm now a lecturer in geomatics, which is a maths of positioning in space at Plymouth University in the UK. And I've published 26 papers proposing this theory, quantized inertia, and also a textbook, which is shown on the left here, and a sci-fi novel about the theory as well, called Falling Up. Okay, so why am I appearing in the Secret Space Program conference? Well, I may have a slightly different understanding of the Secret Space Program to most of you. So I'm not saying that I believe there is a major space program deliberately underwrapped, but I do believe that work on radical new propulsion or energy technologies is being suppressed in a possibly emergent and subtle manner. So it could be simply academic inertia, that kind of thing, or it could be something more organized. I don't know, but I have evidence for this. For example, when my work started to become noticed in 2012, I noticed a real pushback. So the archive that physicists depend upon, we all put our papers up there for other physicists to read. At that point, they started banning some of my papers, even some of those that I'd published in peer-reviewed journals. Very high-level peer-reviewed journals were banned or not accepted by them. UK universities now refuse to let me speak, and people have told me that this is because I make them feel uncomfortable. But I'm not sure whether this is because of QI or because of some of my political views. And in the past 2 years, journals have changed behavior. They've started refusing my papers without substantive comments, which is interesting. Okay, so back to the science. So the problem that I started thinking about was the galaxies spin faster than physics predicts. So here is a galaxy, this yellow disk here spinning around. And if you look at a star within it, astronomers can determine its speed and the centrifugal force acting on it. And they can also see how much matter is in the galaxy, which tells them the gravitational force pulling it in. Now, from the data that's available, it seems that the centrifugal force is much greater than the gravitational force, so galaxies should fly apart inertially, but they don't. So this was first noticed by Fritz Zwicky in 1933, and then by Vera Rubin in 1980 in more detail. So what they normally do is they increase the amount of matter in the galaxy. They put a lot of invisible matter in there to boost the gravitational force so it balances the centrifugal tendency outwards. But I don't like this dark matter solution because it's arbitrary. They just add it where it's needed to make the theory work, and that is not good scientific practice. So I've been thinking about inertia for a long time, about 18 years now. Inertia has never been understood. It's just been assumed that things keep going in a straight line until you push on them. Inertia is not due to the Higgs field, which only explains a tiny proportion of mass. But I proposed a new model for inertia, combining relativity and quantum mechanics to explain why things do keep going. Okay. So this is a schematic showing the model. So here in the center, we have an object, a black sphere, black disk, which is accelerating. We imagine it's accelerating to the right. And according to Fulling, Davis, and Unruh, back in the 1970s, when objects accelerate, they see what's now called Unruh radiation. And I've tried to represent this with the red color here. What also happens, and we know this from relativity, is that when things accelerate, say, to the right, information from the left cannot catch up with them. And so there is a kind of a shadow zone that forms that this object will never be able to perceive as long as it's accelerating. And at the boundary of this, there is a horizon beyond which we cannot, this object cannot see. So the new part of quantized inertia, the thing I'm suggesting that's new in quantized inertia, is that this horizon damps this Unruh radiation. So whereas over here, the Unruh radiation is warm, a warm thermal bath of radiation, near the horizon it's much cooler because it's been damped. This means that more radiation is hitting the object from in front than from behind, so it'll get a pushback to whatever acceleration it has. And I managed to show in this paper in 2013 that this predicts inertial mass really well. Okay. So just to show that Unruh radiation is not just some theory, it was actually confirmed last year. So Lynch et al. 2021 looked at what they did was they slammed high energy positrons into a silicon crystal, and they saw radiation coming off, and they managed to show that the spectrum of the radiation looked just like what you would expect from Unruh radiation. So they published that here. So Unruh radiation is a real thing and has been seen. Okay, so this explains standard inertia, but this theory also makes a very small modification to it. So imagine that the acceleration is extremely low. As the acceleration gets lower and lower, the Arundal horizon, the point from which information cannot catch up with it, moves backwards. And at some point, the Arundal horizon will move back behind the cosmic horizon, which is the horizon at the edge of the cosmos beyond which we can't see for various reasons. And at that point, the Arundal horizon will no longer be producing an asymmetric damping on this object. The damping will now be symmetrical all around the object. And this means that inertia will collapse for very low accelerations. And I showed that in this paper in 2007. And the formula looks like this. So the modified inertial mass is equal to the original standard one times this factor, which is 1 minus 2 times the speed of light squared, divided by the acceleration of the object times the cosmic scale. And you can see that normally this term, 2c squared over a theta, is very small because this theta is a very big number. But if the acceleration is very small, this term blows up and reduces the inertial mass. And this is great because at the edge of galaxies, where the problems are with these dynamics, the acceleration is incredibly low. The stars are moving with incredibly low acceleration. And when you apply quantized inertia to the stars, it predicts that they lose inertial mass, and so they lose centrifugal force. And this means that there's now a balance between a smaller centrifugal force and a gravitational force. And it predicts galaxy rotation perfectly. And I showed that in a paper in 2012 here, and also in this paper in 2017, where I compared galaxy rotation data with the theory. So this is the expected acceleration along the x-axis. This is the observed one. And the gray squares show the data. So for low accelerations, the observed acceleration is much greater than you would expect. This is the galaxy rotation problem, and quantized inertia predicts it. It's the dashed line there. And the equation it predicts is this one. So the velocity of the stars at the edge of a galaxy to the power 4 is equal to what's shown on the right-hand side. And the interesting thing is that there is nothing adjustable in this equation. So it has one chance to work, and it does. It predicts perfectly. Nothing here can be adjusted. Okay. Further evidence of this is shown here. So we have a galaxy spinning around like this orange disk. In the center, the acceleration is large, so the unruh waves seen by stars are short. As you go out through the galaxy, the unruh waves get longer. And at exactly the point at which the unruh waves become equal to the cosmic scale, that is the point at which the galaxies start to misbehave. So that implicates unruh radiation in this galaxy rotation problem, and therefore quantized inertia. Okay, so if this means that we now understand inertia, then that means we can control inertia, something we have never been able to do before. And I proposed ways to do that in this paper in 2013 and a later paper in 2018, and more recent papers as well. But the upshot of it is that if you have what I call an accelerand, a highly accelerated object shown by these arrows here, then they will see unruh radiation, which I've shown with the red. Now, if this object accelerates fast enough, then the unruh radiation will have a wavelength which is quite short, so shown here, and then it would interact with, say, a metal plate that was put close to the object, so a damper, if you like, and this is a damper here. This would mean that the damper will reduce the unruh waves in this direction, so now this is very similar to a horizon, because the metal plate is damping unruh radiation close to it. And this means that the accelerand will try to move down the gradient, because more unruh radiation will be hitting it from this side than it will from this side. So it will move. Now, this is a new way to move things, because normally, in order to move this up, we'd have to use explosions to fire molecules downwards so that the momentum conservation will push it up. This doesn't need that. It's a far subtler way to do it. So because we're using what's effectively a synthetic horizon, I've called this a horizon drive. So I proposed this in some papers here, as I said. Okay, so as soon as I started saying things like this, I was contacted by DARPA, and I applied for funding, and I was awarded $1.3 million to demonstrate this in the lab. So my project aims to demonstrate scalable thrust from quantized inertia in the lab, thrust that we can scale up to do useful things like move satellites around or even launch things. So I've been working on this project for 4 years now, and we've learnt a lot. We've learnt both what to do and also what not to do. So the first experiments involved the accelerand in that case was photons. So we tried to trap photons inside very small, quite small cavities to see if, and asymmetric cavities as well, to see if that produced a force, but the thrusts were too small or zero. So we concluded this is not a viable route. Then other labs showed that electrons might be more effective. And we have now moved this way. And I think we now understand theoretically why this should be. So this other lab was Frank Becker and Anke Bat, who had read my papers, and they decided to try a capacitor setup because they had experience with that sort of thing. So they had a capacitor with cathode, anode, and dielectric between. They put it on top of a digital scale, and they charged it up. And the idea here was to accelerate electrons hugely over the gap, over the dielectric, so that they would see very short unruh waves, which might interfere with the capacitor and produce thrust. And indeed, they saw thrust. This is a plot showing the the data. So this x-axis is a separation of the plates, and this is normalized force at the y-axis. So when the separation of the plates was about 100 micron, this force was small, about 0.1 millinewton, millinewton. And when the separation was about 10 micron, the force was much larger, getting close to 10 millinewton. Now, the great thing about this is that if we can scale this up, this is very scalable. So if you can put a kilowatt of power in, you can get 100 newtons. And this is much better performance than you would get from an ion drive. The ion drives used on satellites give you about 0.02 newtons per kilowatt. And also, in this with this capacitor drive or horizon drive, propellant is not needed. So you don't need to carry fuel. You just need a solar panel to give you electricity. So why does this work? Well, this is my explanation. So if you have an electron accelerating to the right, then normally in quantized inertia, the electron sees a lot of unruh radiation in front of it because there's no horizon, but behind it there's a horizon, a Arundal horizon, which damps the radiation. So it gets pushed back. It tries to go down the gradient from red to blue. But with the capacitor, when you accelerate an electron from the cathode of the capacitor plates completely damp, or almost completely damp, the unruh radiation between them. So now, again, you have blue behind the electron, but now you've got a virtual black zone here. So the electron actually gets a push forwards. Its inertial mass is reversed in a sense. So you get an extra push that way, and then it hits the anode and pushes it. And this kind of mechanism predicts very well what Becker and Batt saw in their experiment. So I published this on ResearchGate, and I'm trying to publish it in the journal now, this theory part. Okay. Also, Becker and Batt, they did this experiment in liaison with me, and they did a very interesting experiment in that what they tried was they put a baffle. So this is the capacitor here with the electrons accelerating across. They put a baffle behind the cathode, and they found that this damped unruh waves more in this zone and pulled the electrons back slightly, which is okay. But then this is the expected position of the Arundal horizon. So this isn't a solid object, but it's a predicted position for the Arundal horizon. As soon as they moved this this baffle back behind the Arundal horizon, then its effect on the electrons disappeared, which is a very good, perfect proof that the Arundal horizon does exist and that it's quantized inertia causing this thrust. Okay. So how do we derive the force on a capacitor from Qi? Well, the way I do it here and in the paper I'm trying to publish is based on the well-accepted Casimir effect. So in the Casimir effect, you have two plates, and the very tiny quantum background is damped between the plates. So you can see this blue region, but not outside. So the plates try to move together. But when you're dealing with quantized inertia and electrons accelerating across the gap, you have to excite the vacuum, because the vacuum is now composed of unruh radiation. So to do that, you just change h bar in this equation to the energy you're putting into the electrons and the time it stays across between the gap, and you get a formula like this. And then collecting terms, you get this formula. So the force predicted by quantized inertia is this number here, which is actually a combination of factors like the mass of the electron and the charge of the electron, times the current that is flowing across the gap, times the area of the plates, a bit like in the Casimir effect equation, divided by the distance between the plates squared. So this is the predictive formula. So does it work? Yes, it does really well. So this shows the separation of the plates. This shows the force. The black diamonds show Becker and Batt's data, and the white squares show the prediction. And these are the error bars. So you can see that it agrees really well within the error bars. And I've published that on ResearchGate here. Okay, so this has also been tested by a company in Virginia called Ivo Limited, mostly by Richard Mansell, who I've also been liaising with. And to try and get rid of digital artifacts, they used a capacitor, and they've tested in a vacuum. So this shows their capacitor in a vacuum, and they have confirmed Becker and Batt's experimental results. Okay, so we are now looking at this at Plymouth as well, and we have a system that we've gradually been setting up. So I've been working with a postdoc, Dmitry Makhnovskiy, and my chief engineer, who is Richard Arundal, who you'll see in a minute. And we've developed a system like this. So we have a digital balance here on a plate, isolated from vibration, things like that. We have a battery. The whole thing actually can work from a 12-volt battery, but the electronics boosts the voltage quite considerably. And the voltage comes in, it goes through liquid metal gallons down into probes which connect to the capacitor, which is shown here. So the cathode and the anode, and the dielectric is normally Kapton or polyethylene, but normally Kapton. So the capacitor, for the plates, we use aluminium foil, and the separation we've tried, it varies a bit. We've tried mostly 7 or 14 micron. The area of the plates is typically 5 by 5 centimeters squared, and the leakage current is typically about 0.1 microamps. Okay, so the electronics was developed by Dr. Dmitry Makhnovskiy. The circuit diagram is here. The capacitor can be charged up to about 3.5 kilovolts. I think we can now go up to 4 kilovolts, and it's done in tiny increments to avoid burnout. And these tiny increments also allow the first detailed analysis of this phenomenon, so we can detect at exactly which voltage the thrust appears. We can also measure the leakage current. So this is one example. This is the high voltage chip output in kilovolts, and this is the load current. So you can see it's usually somewhere between 0.1 and half a microamp. Okay, and the testing system itself was developed by with liaison with everybody, but mostly by Richard Arundal, the chief engineer. So he's built a new physical test stand, improved physical shielding. We've worked to eliminate electrostatic artifacts in the system. He's improved capacitor manufacture and the systematization of data recording. So we keep very close records now. And he's also helping to build online awareness. So he has a YouTube channel on which he publishes a lot of the experiments we do. And we've completed 90 tests in 10 weeks. So this is Richard here. Okay. So some of the results. So this is a summary, an average of the results that we have that we think are clean, so that they don't have drift in them, because sometimes digital balances are subject to drift. So this shows the voltage applied in kilovolts, and this is the thrust towards the anode. So the theory predicts that the thrust in most cases should be towards the anode, but if you vary the capacitor plates, if it's asymmetric, then that might change a bit, and it does change in some cases. So positive is towards the anode. And the data is shown by the black curve here. And the interesting thing is that if you look at the breakdown voltage of the Kapton, and I've shown that here for the 7 micron Kapton with this bar here, and for the 14 micron Kapton with this sort of red bar here, this is where we expect the effect to appear, because when the dielectric starts to break down, that is when the electrons start to accelerate across, and that's when we'd expect the thrust to occur. And if you look at the black curve, that is indeed where the thrust starts to occur. You can see there's a peak here for the experiments that used 7 micron, and there's a peak here for the experiments that used 14. Okay, so in our experience so far, most runs, about 77%, produce no thrust. 23% of them produce a thrust of various kinds. 17% produce a thrust towards the anode, which is what the theory predicts. Some of these that produce a thrust towards the cathode had a different setup, so different foils, one foil aluminium, one foil copper. So that may well have reversed the thrust. We have to analyze that. But the interesting thing is the peak for the 7 micron Kapton and the peak for 14 micron. So it appears that something is definitely there, but we can't say for sure yet because the uncertainty, this is the standard deviation, is much higher than the data so far. So this is just a breakdown of what thrusts we have. So this is the observed mass change in milligrams along the x-axis. And this is the predicted one along the y-axis. So hopefully what we will be seeing, the ideal, if the theory is right, we'd see a lot of data over here. And we do see some. You can see that this was our best test. This was run number 76. So we got 20 milligram, about 20 milligram of thrust. 38 was also a good one. These are not bad. We did use a different scale at one point, which was unable to see a lot of the finer thrusts, smaller thrusts. And so we do have some variation when we use this scale called Adam. And there were a lot of tests that produced nothing, and there were some tests that produced a negative thrust, but most of them were producing a positive thrust towards the anode. Okay. So what does this mean? So if we see, say, 20 milligrams of thrust, what does that mean in terms of compared to ion drives? Well, if we look at the Dawn spacecraft, which had an ion drive on it and went to the Minor Planet Ceres in the asteroid belt, its ion thruster produced 90 millinewtons of force, but it had a weight of about half a ton because of, well, various things, but also it had a lot of propellant, nearly half a ton of propellant on board for the ion thruster, and it needed a lot of power. But it went from 0 to 60 in about 1 or 2 days. So far in Plymouth, we've seen 0.2 millinewtons, which is less than what the Dawn ion thruster produced. But it only has a very small weight. If you build a spacecraft from it, it would only have a weight of maybe 3 kilograms, because it won't have to carry propellant, just solar panels. And it needs less than a watt to power, and it goes from 0 to 60 in 5 days. So this is much better. Okay. So applications of quantized inertia are fairly obvious. At first, it will be used for satellite station keeping, use on CubeSats, for example. It would mean that satellites will be much lighter to launch because they won't have to carry fuel. Later, of course, flying cars, things like that become possible, structures that hover. Even launches, we hope to replace rockets. And also another interesting feature of this is that normally rockets expel propellant, of course, and that there is a whiplash effect as you're pushed back in your seat. This kind of propulsion is different because a horizon drive would accelerate every object in the spacecraft equally, so there'd be no whiplash. So you'll be able to accelerate far more rapidly and still live to tell the tale. Also, as I'll discuss in a bit, this means that we can get energy from the vacuum, and also interplanetary and especially more uniquely interstellar trips become possible because you don't have to carry fuel. Okay. So I promised to say something about energy, so I won't say much, but I'll just give you the gist of it. So for chemical rocket, energy is conserved, of course. So you have rocket going this way, you have a lot of expelled fuel going that way. So the kinetic energy and the momentum is all in balance. But if you have a QI rocket, which is moving to the right here, but nothing is apparently coming out of the other end, people will quite rightly conclude that there is no ejected material. So how is the energy being balanced? you can work out the electrical energy that you're inputting to this rocket here, which is proportional to time, but the kinetic energy it's showing is increasing with time squared. So where is the energy coming from? There's some extra energy coming in. Well, you can show that this extra energy is coming in from information. So there's something called Landauer's principle, which says that if you delete one bit of information, then you get an amount of energy out, which is equal to kT times log 2. If we delete n bits of information, we get kT log 2 to the power n, which just simplifies to ktn. So this means, and this has now been seen in by experiment, that every time you delete information, energy has to be released, and this is to keep entropy from decreasing. If you delete information, you reduce entropy. That can't be allowed, so you have to release heat to increase the entropy again. So if you apply this to an object, so I've shown an extended object by this black dashed line, then before it accelerates, it will see a cosmic horizon, and it will be able to see a lot of bits of space. So I've assumed that each Planck length of space contains one bit, because this is the smallest region of space you can detect or observe. So beforehand, this object could see all these bits of space. Afterwards, when it accelerates, a Arundal horizon appears, chopping off this part of space to the right. So now it can only see these purple bits of space, fewer bits. So all this information has been erased, so you have to get some energy out. And if you calculate how much energy and then mass you get out, you get this formula. And you may remember this because this is the formula for quantized inertia. It's the same, and it's a formula that predicts galaxy rotation as well as all this thrust. So the extra energy is coming from the erasure of information as these horizons are formed, and I discussed that in this paper here. Okay, so to summarize, quantized inertia, it explains inertial mass for the first time. It brings information into physics, as I've just discussed. It gets rid of dark matter and also dark energy, because it predicts cosmic acceleration as well. It has excellent astronomical evidence from galaxy rotations, observed galaxy rotations. QI predicts a horizon drive or electric rocket, and it's been shown that the capacitor thruster is the best approach to use. In our lab, we're seeing thrusts of 0.2 millinewtons, that sort of order so far, but this can be enhanced. And quantized inertia is also a potential energy source. Okay, so that's it. Thank you to Paula Messina and SSP for inviting me. Any questions?